I've been in AppSec for about 12 years, mostly web technologies, and about 6 months ago I decided to try and take a stab at AI, with it being all the rage lately. And so this talk is really my experience with it and just try to shed some light on the taxonomy with AI systems. So the talk is titled Neural Nets and Flying Saucers. Just to get us started, we'll set the tone with an agenda here. So I'll start by briefly talking about the UFO Reporting System. So this is like a damn vulnerable machine learning application-esque test bed that I developed. I usually use it for just testing like emerging technologies. It started as a kind of a pet project to teach friends how to hack web applications and family, and it just evolved into just a test bed for AI and ML stuff now. We'll jump to a brief introduction to ML so that we can understand the attacks that I'll be demoing in the application. And the approach that I'm going to take is it's a build it, hack it, patch it type of approach. So I'll show how machine learning engineers would actually go about developing some of the models that I implement in the app, and then we'll attack it. And if we have time, we'll talk about some mitigating controls. So the UFO reporting system, it's Docker based. You'll be able to pull the Docker containers today. It's a Flask-based application, SQLite database, and it has another component. It has a fast API component, and this is the inference API, right? This is the API that I use to make inferences and some of the features within the app. I was actually going to demo it now briefly to cover the whole premise of it, but it's just going to be too much. My entire talk is almost is a demo, really, so it's going to be too much switching back and forth. So I'll just jump right into the introduction to ML. In my experience, I think it helps when we try to figure out what AI is and how programmers use machine learning in their day-to-day. I think it helps to compare it to traditional programming, right? So if we take this example here, say we want a developer to build an app to tell us whether or not someone was speeding, right? So in this case, you'd give the developer the speed limit, you tell them the distance traveled, and they should be able to tell you whether or not someone was speeding. So if we take a look at the code here, it may not be good to see here, but if we take a look at the code, it's fairly simple. Like we understand this problem, right? And if we understand a problem, we know how to solve. We can write a solution to solve it. So here's a basic Python function. It accepts distance in miles, time in hours, speed limit. It calculates the average speed by dividing the miles by the time. It checks whether the average speed is greater than the speed limit and returns true or false, right? Whether or not this person was speeding. It's fairly straightforward. It's a heuristic-based solution to a problem that we understand. But now say we ask the same developer, I give you an image of a car, and you need to tell me if that car is damaged. Oh, and I need you to rate that damage from minor, moderate to severe damage, right? This problem gets complicated quickly because the developer will realize that there's really no feasible way to write a heuristic solution to that problem. We all know that we see a damaged car, we know where the car is damaged, we can take a stab at trying to classify it between minor, moderate, and severe, but we have no idea how our brain does that, right? It'll be really difficult for us to write a heuristic solution to that problem. And it turns out that that's a problem that's more, that's tailor-made for machine learning. Because whereas in traditional programming, we define the process or a function to turn inputs into outputs, machine learning uses inputs and sometimes outputs, if we give it to them, to derive the process or the function itself, right? So it's not far-fetched to say that machine learning generates functions to solve world problems, right? Or models, also known as functions. So in this case, we will provide it an input, an image. We provide it a label, severe, moderate, minor. We use machine learning algorithms. In this case, I'll show you neural network. And that machine learning algorithm generates a model, or the function that we then use to make predictions on new images. So let's solve that vehicle damage classification problem using machine learning. At a high level, machine learning, there's two types of learning, right? There's supervised, unsupervised. Supervised learning uses labeled data to learn how to classify input. Unsupervised learning uses unlabeled data to find patterns in our data. And there's several algorithms that we can use within those two learning paradigms. Today I'm going to demonstrate supervised learning, and we'll use classification and a neural network within classification, rather, the neural network algorithm. So let's see. Okay. Yep. So we'll solve this problem with machine learning, supervised, classification, neural network. And before we jump in, we'll at a high level cover what a neural network is and kind of how it works. This was the best example that I could find that covers my exact use case that I'm going to be demoing. It's exactly the same thing, only they're doing shapes and not vehicle damage. But so neural networks are inspired by the structure of the human brain, right? It'll take in data and it trains to recognize patterns in that data, and it creates a model. It consists of several layers of neurons, and neurons are the core processing units of that neural network. The first layer here is the input layer. In this input layer, we'd have 784 neurons, because each neuron corresponds to a pixel in the image that it's receiving, right? It's 28 by 28 pixels, so 784 pixels or neurons in total. The output layer consists of 3 neurons. Each neuron tells us the classification, right? So in this case, square, circle, or triangle. In our case, it'll be minor, moderate, or severe damage, and that's the output layer. The layers in the middle are the hidden layers, and these perform the majority of the computation, so like deciding which neurons get activated. So as data passes through the network, I should mention that each neuron is connected through to the neuron in the next layer through channels, and each channel is assigned a weight. Right, and each neuron in the hidden layer is assigned a bias. So as our input traverses the neural network or feeds through the neural network, the values from the previous layer's neurons are multiplied with the corresponding weights and added to the bias, and then the sum of that is passed through an activation function that decides whether the neuron in that layer gets activated. And so that occurs for every single neuron or every single layer until only one neuron in the output layer is activated and decides whether or not, or decides the classification for that image. So notice that in this first training iteration, it actually misclassified the image. It thinks it's a square. And we get a loss. So the loss is just a difference between the predicted value and the expected value, and we use a loss function to calculate that. The problem is that the loss only gives us the magnitude of the error and not the direction of the error. So for that, we need to calculate the gradient. The gradient gives us a sense of direction of that loss. So if the loss is the difference between the predicted class and the actual class, a gradient tells us how much the weights and the biases need to be calibrated or tuned so as to increase the loss. But we don't want to increase the loss, we want to decrease the loss, so we go in the opposite direction of what the gradient tells us. And then the network iteratively updates the gradients and the weights and the biases in the direction that reduces the loss, so in the opposite direction of the gradient. And this process is known as gradient descent, right? And the neural network will complete that for each batch of data, which is the minimal samples of data is used to compute that gradient for the entire data set. And it'll do that until we have a model that can accurately predict the class, right? So if circle is equal to a circle in this case. Yep.
Is the ideal the high side or low side of the gradient? Am I guessing low side 0 because it's a gradient descent going down?
So you mean these here? Or did you say the 0?
Yes, in terms of your direction you're going, is that up or down?
The ideal is the target.
No, go ahead, please do.
Ideal is the top.
It's the target. It's the target. So it could be up, it could be down. The point is you have a target, right? Whether it's so he's showing a nice graph over there.
I just wonder if descent means going down towards 0. Is that part of it?
So the gradient is a vector that is a vector of derivatives that tells us the direction of the law. It's a measure of the steepest point of that loss function. But because we don't want to increase the loss function, we use that as an indicator to just go the opposite way of the gradient. And so we update all of our weights and our biases in the direction that's opposite to that gradient. Okay, so I'm going to demo what a typical machine learning engineer would go through to develop a model like this. Okay, and so now I'm going to just switch back to sharing my screen here. And then the rest of this talk is really just a demo.
That's kind.
Just bear with me for a second. I'm trying to duplicate my screen here. All right, cool.
Hey John, I see it's working, so what sacrifice did you make to the demo guys?
Yeah, it's none. So
Fucking hell.
I do own 3 cats though, so maybe that's it. All right, so this is a Jupyter notebook. If you're not familiar with this is like a machine learning engineer's IDE. So if you use Visual Studio Code, for instance, this would be the Visual Studio Code for machine learning or a data scientist. And it's pretty cool because you can run Python independently of all of the other blocks of code here. For instance, I have all of my imports here. I'll run that once, and it's all stored in memory. And then I can add text, right? And it's all just markdown. And it's all of the Python objects are stored in memory, so I can just go through this individually and kind of just explain how this all works. So the first step here is data acquisition. This is the most important step because the quality of the model that you end up generating is directly proportionate to the quality of your data. There's a ton of places you can get data. You can create your own, but obviously it's expensive. Before, like years ago, companies would have to gather all of this data themselves. Today there's a ton of open source data repositories. For instance, there's Google's data search or dataset search. There's the AWS registry of open data. Azure, Microsoft has some open data sets. Data.gov for government data. There's OpenML, RoboFlow Universe. The data set that I'm using for the demo is from this repository, but the point is there's a ton of repositories out there where you can get data sets, and the barrier of entry to get into this and start researching is low. If you're using Google Colab, so like this environment here to train machine learning models, you can mount Google Drive to access your data. So I'm just going to show what that data looks like or what our data set looks like for this sample. I have about 5,000 images here of vehicles, and then I have a CSV file. Let's see if I could make this. All right, here we go. All right, so I have a CSV file that consists of the file name and then a one-hot encoded, which means each column is a binary indicator of whether this image was minor, moderate, or severe or damage. So the first thing we do here is mount that drive with that data set that I just described. The data set is actually a zip file. We then extract that zip file. And then we do data pre-processing. This is probably the second most important step in the machine learning DevOps. This can have significant impact on model performance. You'll make decisions like if your data set is too large, should we sample a fraction of the data set? If the data set is too small, should we find ways to augment that data set? Do we have data that needs to be encoded? For instance, in this case, if this data set had a file name and then another column with damage and the labels were all like qualitative labels, so like minor, moderate, and severe, we would have to one-hot encode that column before we can feed it into our model, because we'd have to tokenize it, right? So if, for instance, if we had unstructured data, we would have to tokenize it and pre-process that data in a way that the model can understand it. So the first pre-processing step here is to join the image directory to the file name and create a full path so that the model knows where to find that image. A few notes here just on augmentation. So this is a way that you can increase the diversity of your data set for free. So as opposed to having like 10,000 images of different vehicles, I could have 5,000 images and just tweak them. I can rotate those images by a certain degree. I could flip them horizontally. I can shear, which means just like turning it on one of its axes. And that way you increase the diversity of your training data set without actually having to get more data. So this just makes your model more robust because it's been exposed to a more diverse pool of images in this case. So the next step here, we prepare training and validation data. There's this concept of overfitting, which means that your model might perform really well on inputs that it's seen already, that it was trained on. So in order to avoid that, we split our data between training and validation data. And so when we measure the effectiveness of our model, we do it with validation data, which is samples of our data sets that it was never trained on. So here we specify the class labels, which is minor, moderate, severe. Batch size, which is 32 here. This is just the minimum number of samples in our entire data set that the model is going to use to compute gradients. We have our target size is just the dimensions of the image that we're feeding into it. And then we have generators for our validation and our training data. So the next step would be to actually build that model. So first we load a pre-trained model. We're not actually going to train this all from scratch. We're going to use EfficientNet trained on the ImageNet data set. This is an open source model developed by Google. So models trained on the ImageNet data set generalize really well to other tasks. And so we could use a base model that was trained for another but related task as a base model for our model, and we can like recycle a lot of the training insights that model gained, right? And this is due to a concept known as transferability. So if the ImageNet model learned that certain shapes and textures and edges, colors, angles, and it learned those features to classify the images that it was trained on, we could actually recycle that for our tasks. So that's what we're doing here. We're setting the base model. We're telling it not to include top. It just means not to include the last few layers because we're going to add our own custom layers on top of it. We set trainable equal to false because we don't actually want to train the base layers. We add our hidden input layers. If you remember, these are like the middle layers that do all of the computation. This is our output layer, which is set to 3, which matches minor, moderate, or severe classification. And then we compile that model with all of these hyperparameters, right? So the learning rate, the loss function that it's using here. The next step is to actually train that model. So the first thing I do here is set the epochs to 10. This is the number of times that model is going to go through the entire data set during training. I have a couple of 2 callback functions here. Early stopping basically just stops the stops training after, I have it. It'll stop training after, I forget where I had the model here, but it'll stop the training if the accuracy dips below a certain point, right? And so that way you avoid continuing the training process and ending up with a model that would have been more accurate had you stopped training it a couple of epochs ago. And then another similar callback function reduces the learning rate in a similar manner, right? So after that, if the accuracy dips after a certain point, it'll reduce the learning rate.
Can you enlarge the text at all?
Yeah, I'll try. Let's see. That better?
Yeah.
Okay, cool. So these are the callback functions, and then here, this is where we actually fit the model, or we start that training process, and this will run for however long it needs to. I'm going to actually share this Jupyter notebook. I stripped it of all of the content that I had just so that it would be easier to demo it, but I have like a lot of context here on what all of this does and what all of these functions do, and some background information also. So then this is just some code to evaluate the effectiveness of that model. So the next step is to fine tune. If we're not content with the accuracy of that model after training it for the first time, we could go back and fine tune it, which means tweaking those hyperparameters to increase the model's accuracy. So the first thing I did here was I made that base model trainable. So I made that base model trainable so that I could start learning on the features of my data on top of the features from the ImageNet database, or data set rather. I lowered the learning rate. I increased the epochs. I had 10 epochs previously, so now it's going to go through the entire data set 50 times. And then we fit the model again, and we evaluate the model again, right? Once you get access to this, you could run this entire notebook, like all of the code in this notebook, and you'll end up with a model that performs really well. So the validation loss is like near zero, and the accuracy on the validation data set is like high 90%. So you could actually use this in like a production application. Let's see. All right, so the next step is just to save that model. I saved it using the saved data format, or the saved model format rather. And you just end up with a file and you zip it. That file includes all of the, let's see, so that file includes the model here, and I zipped that file up. And now I'm going to show what that looks like in the app here. All right, so this is going to be super risky here, but let's do it. All right, so this is the app. This is the Flask application, and then this is the API. This is the inference endpoint to predict vehicle damage, and all we do is we load that model that we just extracted. So here I'm loading that vehicle damage classifier, and then I'm using that model to make predictions, right? So here I feed that model the image that we get in this endpoint, and we make predictions, and we return whether or not, or if it was minor, moderate, severe damage, and when we also add a confidence score, right? So like how confident was the model that it was the class that it thinks it is. So I'm going to open up the app now, log in. All right, so this is the app. I tried to make some updates to the color schemes here because I knew it was going to be terrible to see. In the Docker container, there's a test user in the SQLite database. You can just use that to log in, or you can create a user. And so you have a couple of features here. The whole premise is that this is a UFO reporting system, right? So you can report an encounter. There's a couple of fields here: date, location, encounter type, and description. You can view all of your previous encounters, and you can update, delete. There's actually there's a admin role that you can log in as, which does other things, but high level, this is it. You view your encounters, and then there's a damage compensation program, right? So if like the premise here is that if you're like your vehicle is damaged by a UFO or something, you can submit a damage compensation. So these are the two encounters that I reported here. And so I want to claim a payout. So I'm going to upload an image. And I see that I was paid out $500, right? So as an attacker, I see this and I'm looking for abuse cases. And one abuse case would be, well, is there a way that I could modify that image so that instead of being compensated with $500, I could get compensated with more, right? So here I'm going to jump back to the deck. So there's several industry frameworks and bug bars. When I first started doing all of this, like for web hacking, you have OWASP top 10, and it turns out that OWASP has a top 10 for machine learning. There's MITRE, has the Atlas framework with several attacks or attack taxonomy. And then NIST recently released the AI ML attack taxonomy paper also. And of course there's the OffSec wiki we saw yesterday. So for the OWASP top 10, they do have a top 10 for large language models, and there is a test case and demo in the UFO reporting system for LLMs. We're not going to cover that today. So this is the top 10 for machine learning. There's several attack types here. The UFO reporting system currently covers input manipulation attack or evasion. It has a demo for data poisoning. It has one for membership inference. And it also has one for AI supply chain attacks. Today I'm just going to demo the evasion or the input manipulation attack. All right. So let's go back to the report generator or the reporting system here. Okay, so we're going to upload the image again. We're going to try to evade this machine learning. We're going to try to evade the model, right? So I guess a naive way to do this would be to open up a program like GIMP or Photoshop and try to add a filter to this original image, which we'll do. I'm going to save this. All right. Export that with our filter. And then to kind of show this here, I'm going to open up DevTools. I'll upload the original image again. And notice here in the inference response, it indicates it's minor, $500 payout with a confidence of 75%. This is the original image. Now I'm going to do it again with the image that I just added a filter to. And notice that now we get a payout of $500, so it didn't actually trick the model. But notice that the confidence score of that inference is lower, right? So then I tried to do that again by superimposing a rec on the original image. So we'll see what that looks like here. Using GIMP, same kind of strategy. I just layered I layered like a rec, an obvious rec to that image. And so now we got severe damage and a payout of $10,000, right? That's not it. That's not it. Okay. Yeah, but there's a problem here, right? If we read here, it says, our AI systems have reviewed your claim. An adjuster will visit to verify the damage against your submitted photo. All right, upon confirmation, a check will be issued to you in the amount above. So this obviously isn't going to get past a human in the loop. So now we can use the concept of gradients to create an image to target that severe classification with modification, with the minimal amount of perturbations to that image possible to get to that target class and hopefully get past the human in the loop check. So if we go back to the Jupyter notebook here, I have some code to do just that. And so let me just go down here. So the first thing we do here is just load our original image. We specify the target class, right? This is a severe class. And then we specify a value for epsilon. This is just a way to, it's just a way to scale the perturbations, and I'll show that. So the first thing we do here in this generate targeted adversarial example function, first we ask the model what it thinks the image is, right? And then we normalize the target label, and then we calculate how wrong the model was by calculating the loss function, or the loss. So then with the loss, we can compute the gradient, right? Because the gradient tells us the direction in which that loss increases the most. And again, because we don't want to go towards that direction, we'll go in the opposite direction. So here, this is where we get that gradient. We give it the loss, we give it our image, we get the gradient for that. Here we're normalizing the gradient, so the gradient would give us a direction or a magnitude and direction of that loss. Here we're effectively just ignoring the magnitude and only getting the direction. And we're adding that iteratively to our accumulated gradients variable here. And then what we do here is we multiply the accumulated gradients in this tensor. We multiply that by epsilon to get the steps that we want to modify that image by, right? So we don't want to make too large perturbations because then it'll be obvious. We want to just modify that image as minimally as possible to get it to infer a severe damage. And so this function will generate the adversarial example. You could probably do this a lot better. I'm doing 10 iterations of this. I think we set that down here somewhere. Actually, might set it up here. Yeah, so I'm iterating through this 10 times. Maybe a better way to do this would have just like a while loop, right? And just have it modify these values dynamically as it gets to that target variable and just kind of stop there. But I iterated 10 times, kind of just hard-coded. And I'll show what it looks like when we upload that image, that adversarial image. So this is the targeted adversarial image. So now notice that we do get the severe, or we get the payout of 10,000. It classifies it as severe with a confidence of 77%. And the image looks relatively unchanged, right? It's feasible that, and realistic that this would pass a human in a loop check, right? It looks similar to the original image that classified as minor damage, yet we're getting a payout of $10,000 and classified it as severe. So just a quick mention here, this is targeted because we know the target class we want to classify as. And so here we go in the opposite, again, we go in that opposite direction of the gradient. But if we wanted to just misclassify it, and we don't really care what it classifies it as, just not the one that it thinks it is, we could change this to go in the direction of the gradient, right? And then in that case, it'd be an untargeted adversarial image.
Can I ask you a question?
Yeah,
So you do have a big assumption, though, that you know
of course.
what the model
Yeah,
is,
yeah.
right? If you don't,
Right.
you can't do that. So
Yeah, of course.
thank goodness.
Yeah. So, right. So the point with all of this is that what I found is that this is really difficult to do in practice, right? Not only is a lot of this stuff just like alien to me, right? But and I had to do a lot of research for a lot of this. But like an actual attacker would need access to your model to compute your gradients, right? Like we're using the model here, like the actual model that we developed and created to compute those gradients. Not only that, like another assumption is that not only would they have access to the model to compute your gradients, but they would also need to have access to like any pre-processing functions, right? Because otherwise the image that they feed into your model to calculate the gradients just won't work. So there's a lot that this assumes that the attacker has access to, and then at that point, I assume they would be able to do worse things. However, if we remember the concept of transferability, where a model trained for a similar purpose can be used as a base model for your model, that can actually be used as a way to turn all of this into a open box environment, right? So theoretically, an attacker could like query your inference endpoint, build a surrogate version of your model, and then calculate the gradients on that model instead, because due to transferability, the adversarial image generated for that surrogate model would likely also work for this other model that's similar in nature.
So I think you nailed it because you started from an open source based model, so anybody could take that
Right.
and do what you're doing, even with the base model.
Mhm.
So it's still very.
Yeah.
We
Yeah.
have to change our ML now because of all of you.
Yeah, so that's actually a good point. Like one way is to query the inference endpoint like indefinitely and build a surrogate model, but another way is like a lot. I literally use an open source base model, right? So I could just use that open source base model to compute the gradients, and the adversarial image generated with those gradients would likely work with this model. I guess that's the majority of my talk for today. I am releasing all of this code. This app is available in Docker, and I'll show how to pull those in a bit. Apart from the damage classifier, this also has a feature called the symptom checker, and this is I'll have the Jupyter files for this as well. But this can be used to show membership inference, right? So the idea here is that a motivated attacker will be able to query this endpoint. Let me kind of show this quickly. You can query this endpoint that analyzes symptoms for like a fake virus here. And they'd be able to compare the confidence scores that the endpoint returns to determine whether or not someone's data was in that data set, right? And so just wrapping up here. Some mitigating controls. You could one is you can use data augmentation to mitigate against this. By training your model against adversarial images, so like you generate adversarial images and then you add those images to your data set and classify them correctly. If someone else does it, their adversarial image should in theory classify correctly because you've already trained it against those images. Another one is rate limiting, for instance, so like not really allowing someone to build a surrogate model by rate limiting those inference endpoints. There's a couple of other techniques like using ensemble models, regularization techniques, and then some input pre-processing techniques. And from what I've noticed, like this stuff changes almost daily. There's like new research coming out on a lot of this stuff, often. And so some of the researchers that I've been following, and just want to shout out Adrian and a bunch of other researchers that I've been kind of getting to. So Will Pierce also, Hiram, and just some links here for extra data. And then learning resources, really the book, not with a bug, but with the sticker, made this all kind of more accessible to me. That's the first book I read when I decided to kind of get into all of this stuff, so I highly recommend it. And I do have a Discord channel for this where I do plan on, really the plan with this app is to have demos and POCs for every single attack on the OWASP top 10 and like other attack taxonomy papers. Right now we have maybe 4. And so if you'd like to get access to the code, this is how you could do it. And I will release those Jupyter notebooks that I mentioned on the GitHub, and I'll drop that into Discord as soon as that's wrapped up. And that's all I had for you guys. Thank you.